then greater than ms of 2d. And therefore, the critical temperature of 3d is certainly greater, maybe equal, but greater than the critical temperature in 2d. Because any time you have a spontaneous magnetization in two dimensions, you get one automatically fit. So this is
Excuse me.
Yes. Microphone. Well, imagine what the loss. Okay. Oh no, you're welcome. Okay. So again, I will not prove this inequality. There is a derivation, not too difficult to follow, if you are interested in the notes. So I will stop like that on the rigorous result, and now we will start approximate method. So I will start with first an approximate method, which is useful to know, although we will see much more powerful method later. But I will start with high temperature and low temperature expansion. So we move into chapter 5. The notes you will receive soon, tonight or tomorrow, no, maybe tonight. So let me start with high temperature expansion. And I will start with easy. One can do that for any model. So first, to obvious identity. If I have a magnetic field acting on one spin, this function is equal to cosh beta h plus sigma sinh beta h. In fact, any function of a variable which takes values plus or minus 1 is linear by definition. It's f of 1 plus f of minus 1 over 2 plus sigma times f of 1 minus f of minus 1 over 2. Verify the sigma equal plus 1 or sigma equal minus 1 is obvious. When you have a variable whose square is 1, any polynomial, any function is linear. So here, if sigma is plus 1, it's cosh plus sinh. If sigma is equal to minus 1, it's cosh minus sinh. Same is true for exponential beta j sigma 1, sigma 2. But, okay, let me write sigma 1, sigma 2. It's, of course, cosh beta j plus sigma 1, sigma 2 sinh beta j, and this I will write as cosh beta h times 1 plus sigma tanh, and this I will write as cosh beta j times 1 plus sigma 1, sigma 2 tanh beta j. Good. So Z, sum over configuration, exponential minus plus beta j, sum nearest neighbor, sigma I, sigma j, plus beta h, sum sigma I, is equal to cosh beta h to the number of sites, because for any site I can get this factor cosh. Cosh beta j to the power L. L is number of links of the lattice. In 2D, L equal 2n. Each point is related to 4 points, but if you count 4n, you count every link twice. Times product on all sides of 1 plus, maybe I could give a name to tench, I don't know if I did that. Yes, I call the first one tau, and the second one, I need my glass if I want to be consistent with the notes, W. So this one I call W, and this one I call tau. Product of 1 plus tau, sigma I. Here product of all pairs of nearest neighbors of 1 plus W, sigma I, sigma j. When t is small, when t is large, I'm sorry, beta is small. I see some just replaced. I just use this identity for every site, every pair, the identities which are above. No? Everybody sees that, or I go too fast?
What is tau?
Tau is tench beta h. W is tench beta j. Okay, so what do? I take the Ising model, and I say for every site I apply number 1, so I get first this factor, then these factors. For every link, I apply number 2, so I get this factor first, times these factors. I hope this is clear. No? Do I go too fast there? If it's not clear, raise your hand. Yes. Pardon? Sum over C is missing. You're right, of course. Sum over all configuration, meaning sum over sigma 1, sigma 2, sigma n. What do I do next? A trivial identity. Sum over all configuration of a product sigma A1, sigma AN equal 2 to the n if each AI appears an even number of times. And it's 0 otherwise. What I mean is the following. Sum over all configuration, all sigmas, sigma 1, sigma n, of the product sigma 1, sigma 2, sigma 3, sigma 1, sigma 4, sigma 2, sigma 3 is equal to 2 to the n, because sigma 1 appears twice, sigma 2 appears twice, sigma 3, no, this one doesn't work. Sigma 4 appears twice, so this is 2 to the n. I could have also more sigmas, but that's obvious, because I'm summing 1 on all configuration. However, if instead of this one I had sigma 5, that would be 0. Because I can always add the configuration in which sigma 5 takes the opposite value. So that's obvious. Good. So you all agree with that? All I'm saying is sigma square is 1, and if I have an odd number of sigma, the sum is 0. So tau and W are small. We expand in tau and W. Well, we have to expand and to sum. I can expand, and I will graphically design one term of the expansion. Each time I take a tau and a site, I put a cross. So this is a term of order tau cube, in which I've chosen this side, and this side. Tau cube. Then I take a term of order, suborder in W, we will see, such this one. Green on green is not so great. I will choose red. These terms, when I sum on the sigma, gives, this is one term. I have represented one term of the expansion of order tau cube times W to the power 4, 5, 6, 7, 8, 9. This is a term of order tau cube W9. Then I have to take sum over configuration of these terms. Answer? Answer is 0 for 3 reasons. This sigma appears once, this sigma appears once, this sigma appears once. So it's 0. Okay, so that cannot work. How can it work? Well, this one is a little better, but there's still one sigma here. So this is still 0. Here is a non-zero term. This term, which is of order tau 4, W 11, is non-zero. It's 2 to the n. So the answer of this is 2 to the n multiplied by power of tau and W, which correspond to drawings which have these characteristics. Okay? Well, in order to stop torturing you, okay? Are you all clear with that? Yes. I will take a simpler case. H equals 0, tau equals 0. So I return to this. No cross anymore. So this is a term of order W11. No tau. How much is this term? 0, of course. There is one spin here, one spin here, one spin here, and one spin here. That's 0. So the only way of having non-zero is to have closed polygons. That's one non-zero. This one is non-zero. I could have here each side is taken twice, but I could perfectly imagine, let me enlarge the lattice a little bit. I could have something like that. Here I would have sigma to the power 4, which is 1. So it's a gain. Therefore, we found Z equal two to the n. This is this 2 to the n. Cosh beta h to the n, sum over, how did I call this? Sum p, w to the power p, g, p of n, in which g, p of n is the number of polygons with p links connected or disconnected with p links on this lattice. Or if you prefer, perimeter P, total perimeter P. Good. Let's calculate a few of these G's. We are not going very far, but it's necessary to see what goes on. It starts at p equals 0, of course. I could have 0 spin. So G0 of n is 1 by definition, because it came from the 1 here. Then p doesn't take all values. The next value is 4, of course. It depends on the lattice. If I can choose a triangular lattice, in which, of course, I could have a triangle of spins. So then it would start at p equals 3. But let's take a square lattice. It's enough. So what is G4 then? cannot have a closed, anything closed before 4. What's G4 for you? A square. How much is G4? How much is G4? Of course, G4 is number of squares, but my square, I can put it everywhere. So I can put the left lowest corner to any point of the lattice, or nearly any point. So it's certainly equal to n, maybe n minus, I don't know, plus something smaller. But it's linear in n. Constant, maybe, it depends. Of course, I cannot put it on the boundary, the left corner. Because if on this boundary, it doesn't work. On this boundary, it doesn't work. So there, order square root of n. But the n is there. How much is G6? Two n, thank you. 2n. Because, of course, G6 is this polygon like that, or polygon like that. So it's the same story. I can put the left corner everywhere. 2n ways, maybe order square root of n. Not allowed. More difficult, G8. G8, there are two ways of having 8. The polygons can be connected or disconnected. And clearly they are more disconnected, which are two squares. If I put two squares, I have about n square ways of doing that, except that if I count all the position of this one and all the position of this one, I will count twice every configuration. So it's about 1/2 n squared. And then, of course, I can have a true polygon of length 8. This has length 8. And they have order n. I will not go on, but you will see how it's important to have found this 1/2 here. We are not interested in Z, but in the free energy. The free energy is log Z. That's F. So it contains first some trivial factors. plus the log of the series. Log of the series W is small, so expand. The first term is, of course, G4, W4. Then there is a term of order 6, G6, W6. Then there is a term of order 8, but there are two terms of order 8. One is G8, W8. I take the log of this. But I can square G4 and divide by 2. Sorry. So this one comes from the fact that I'm expanding the log of a sum. Clear or not clear? I'm expanding log of 1 plus W4 G4 plus W6 G6 plus W8 G8 plus etc. And I'm saying if I expand the log, I first have these terms, then I have this minus 1/2 the square of these terms, which gives me a term of order 8, which is this one. So what can I say about that? Well, I expect the free energy to be extensive. That's fine, that's proportional to n. That's fine, it's proportional to n, it was 2n. That's fine, G4 is proportional to n. G6 is proportional to n. G8, no. G8 is proportional to n squared. However, you see that we are not finished with the W8. There is minus 1/2 G4 squared, and clearly G8 minus 1/2 G4 squared, the term of n squared disappears, is of order n. It's not of order n squared. So you see that in order to do the right calculation, you have to be careful with these correction terms so that at the end, and don't make mistakes on combinatorics, so that at the end you do get an extensive result. Okay. So we will stop at this level for 5 minutes. And we'll go on to see what can be done with these calculations. So I will keep all this. Positive interactions, attraction, new attraction between spins to the Hamiltonian. The magnetization increases because the derivative with respect to J's was positive. So I'm saying we go from 2D to 3D by adding vertical interaction between the planes. So I can think of 3D by cutting all the vertical links. Then I know that I have a spontaneous magnetization, it's non-zero. Then I add attraction in the vertical direction, the magnetization has to increase. So it cannot be zero. So whenever the two-dimensional system is ordered, we know that the three-dimensional system at the same temperature will also be ordered.